Welcome back to International Finance. I am Andy Kim, your Dr. Finance. In this video, we're going to brush up our memories about option pricing basics in whose underlying asset is just the stocks, because we want to move down to the foreign exchange futures options, right? And then we're going to brush up our memories in the mathematics as well. So here is one example here. Let's see one stock option, call option, whose strike price is $21 per share, and then maturity is 3 months from now. So now and 3 months. Then currently the stock price is $20 per share. 3 months from now, let's simplify the world so that there will be only two states of nature, which is up or down. 위 아래, 위 아래. Upstate $22, downstate $18, right? Then the call option value at the end of this maturity or expiration date will be what? In upstate, 1, because 22 minus 21. Downstate, 0, because you choose not to exercise it, given that stock price minus exercise price will be negative number. So 0. Then the question becomes, today, what's the value of this call option? We assume no arbitrage in financial market, law of one price and all these kind of things. And there are only two states of nature in the world. How do we calculate or value this call option? Okay? Well, we set up a portfolio of stock and the options in such a way that there is no uncertainty about the value of the portfolio at maturity, right? i.e., the same value in two different states of nature, okay? Perfectly hedged in that sense, right? Whether it is upstate or downstate, let's say this portfolio with your call option and then stock will give me the same cash flow, okay? Same cash flow. We don't know the cash flow right now, but it should give us the same cash flow no matter what, okay? Then the thing is, this portfolio with stock and option, call option, is essentially risk-free because it gives me the same cash flow regardless of the states of nature. Same cash flow no matter what happens. That is our definition of, consistent with our definition of being risk-free. So what's the benefit of that? What's the advantage? Well, risk-free cash flow, once we figure that out, we can discount this at risk-free rate. And that will be the value of our portfolio over here, right? It's like a covered call position. And then once we figure out this value of this portfolio, then we will be able to solve for this call option value. Of course, for that purpose, we need to figure out this unknown called delta or hedge ratio. Okay? So let's go to the next slide to figure this out. So, portfolio. Long delta shares of stock and a short position on one call option, as you see over here, right? Long positive delta times S0, short minus 1 times call option C0. We don't know the call option value right now, but let's just set up the math in this way, right? This is a portfolio like covered call, and then figure out this delta first so that the portfolio will be risk-free in 3 months from now, upstate or downstate, okay? We don't know the cash flow precisely at that 3 months from now, but we're going to get there. At maturity, the portfolio value will be either, what will happen? Upstate, it will be 22 times delta, right? 22 times delta minus 1, because there's a call option that we shorted, right? And then that call option value at the end of 1 in upstate is 1, right? Now, how about downstate? It's going to be, the portfolio's cash flow will be $18 times delta minus 0, because call option value at that state will be 0. Okay, so that's 18 delta. These two should give me the identical numbers, identical cash flows. Our setup was that the cash flow of this portfolio at the end of maturity should be identical, risk-free, no matter what. So set up the equation so that these guys will be equal to each other. Then there's only one unknown, which is delta, right? So delta, if you do the math, you will figure out that it should be a quarter or 1/4. And this is called a hedge ratio, okay? Or option delta, right? Later you will, in your derivatives class, you must have learned about this. So the riskless portfolio should be longing 1/4 share and shorting 1 call options. Now what? The hedge ratio, one more time. The ratio of underlying asset that makes the portfolio of long position in an asset and short position in the call option risk-free. Okay. And then portfolio, I told you about this, right? Once you figured out the hedge ratio, stick in, right? And it's time to figure out the cash flow at the end of maturity so that you will be able to discount it at the risk-free rate and bringing it to the present value, right? So you do the math, you figure out that should be 4.5. Just to check your intuition, in upstate it is again 4.5. The cash flow from this portfolio is risk-free. No matter what happens, gives me the same cash flow. Happy, risk-free. Now we can legitimately use the discount rate of risk-free rate to get to this present value of this portfolio. Don't forget, right? This is just the present value of the portfolio, not the call option yet, right? The portfolio value today should be 4.5 discounted at risk-free rate, and then this is 3 months, and the annual risk-free rate, let's assume it to be 12%. So the quarterly risk-free rate will be only 3%. Good. Now 4.5 divided by 1 plus risk-free rate 3% should be 4.36989, and in continuous compounding, right? If you're continuously compounding your interest, then it should be e to the power of minus 3%. For this part, just wait a couple of slides later. We're going to go through the math basics a little later. And then if you do the math, the present value of this portfolio will be 4.367. Okay. Based on this, we can solve for the call option value today. Final destination C0. All right. So we have the portfolio information, which is delta, which is quarter, times stock price today, which is 20, multiply 5, and then minus 1 call option that we just don't know. The present value of this guy should be 4.3667 or 4.367. It's a rounding up error. Anyway, so if you do the math, you will figure out call option value today should be 63.3 cents or $0.633 today. Okay? Here, notice, okay, in this very basic setup, we did not have to worry about the probability at all, right? Upstate 90%, downstate 10%, or the other way around, or 50-50, doesn't matter, right? The probability did not affect anything over here. Now, the slide over here is more of a summary of what we did over the last couple of slides with much more mathematical notations. Instead of throwing in the numbers like this, here, right, the slide over here shows more mathematical notations. So instead of $22 at the end of the maturity, we have S1 up, which is really today's stock price times up rate. And then S1 down is instead of $18, right? That's S0 times D, okay, down rate. And then C1 up, C1 down, and S0. And then remember, we were constructing a covered call portfolio so that we will have risk-free cash flow in the future, so that we will be able to, once we figure out the cash flow in the end of the period, we will be able to discount it at risk-free rate. Very convenient. Then figure out the call option value today. The key question becomes, what's the delta hedge ratio? Okay, that's this guy. Now, some mathematics refreshers are here. Remember, I told you that there was a e to the power of 3%, right? Kind of things. It is assuming continuous compounding, right? Compounding your interest at every millisecond. And remember the definition of natural log e? Well, that was limit sending n to the infinity, where these, 1 plus 1 over n to the power of n, right? The number that is infinitesimally getting closer to 1 and raising this to the power of infinity. Would it explode to infinity? And the answer is no. And this number turns out to be irrational number, 2.718281828, blah, 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 blah. And people are still trying to find out the digits of these numbers, right? Anyway, in fact, this is coming from one more general functional form, which is e to the power of x. And that is nothing but 1 plus x over n, raising it to the power of n. Okay? Now, send the n to the infinity. You borrowed, let's say, with this idea, let's go back to our time value of money kind of questions in your Finance 101, okay? Your borrowed amount is principal P, big P, and then interest rate is R per year. At the end of 1 year, you pay what? Big P times 1 plus R, right? But if you are compounding every 6 months, at the end of 1 year, you will repay what? Compound it twice, rolling 2 times, right? So 1 plus R divided by 2, right? Half year rate, raise it to the power of 2, which is like square it, times P. That's what you owe. If you are compounding every month, right? Monthly compounding, then what happens? Well, P times 1 plus R divided by 12 and raise it to the power of 12, right? If you have to compound every day, 365 days, right? Then P times 1 plus R divided by 365, raising it to the power of 365, right? Okay, that seems fun. If you have to compound every millisecond, then what? Well, you just replace this 365, okay, by n, and send this n to the infinity. Okay, so P times this whole ugly term, which will be, e to the power of R times P. Okay, should be it. And for example, annual interest rate is 12%, then what? Well, that will be P times 1.1275. Notice that this is slightly bigger than 12%, right? And if you adjust the maturity by a fraction, t, then what happens? Well, P times 1 plus R over n, raising it to the power of n, and then the maturity by a fraction of big T means like raising it to the power of big T. And then the law of or property of this exponent works like this: multiply R and T, right? By T, right? For example, annual interest rate is 12%, but the maturity is only 3 months. Then what happens? T should be 1/4, right? 3 over 12. Hence, what happens? Well, P times 1 plus 12% over n, raising it to the power of n, then raising it to the power of 1/4. That means e to the power of 0.12 times a quarter at the exponent level, so that it becomes e to the power of 0.03. That is this guy. Okay? Notice that this is slightly bigger than 3%, right? Okay. This time, let's calculate present value of some amount you get in 1 year. You have a zero coupon bond that will pay you X dollar in 1 year with an annual interest rate of R. The present value of the coupon would be X divided by 1 plus R. If your ZCB, zero coupon bond, does compounding every 6 months, what's the present value? Well, X over this guy, or X times this to the power of minus 2. Your ZCB does compounding every month, well, X times this guy to the power of minus 12. Good. The present value seems like what? Raising it to the power of minus something. Ooh, okay. Now, your ZCB does compounding every day. Okay, raising it to the power of minus 365, right? And then compounding every millisecond, you guessed right. X times e to the power of minus R, which is really coming from here, right? This guy should be e to the power of R, but that's in the denominator, so that's why we have minus over here. Okay, present value is e to the power of minus R. Okay, if you adjust the maturity by a fraction, big T, then what? Oh, e to the power of minus R times big T. That's it. Ooh, if you do the math, you will realize it. Okay? For example, annual interest rate is 12%, but the maturity is only 3 months. That's big T being a quarter. Hence, present value of your zero coupon bond will be X to the power of, X times e to the power of minus 0.03. That's this guy. Okay? So, if we denote the risk-free rate by R and period as big T, the value of the portfolio, okay, value of the covered call portfolio, which is supposed to be risk-free in the future, right? Well, the present value will be like this. Oh, that ugly term got in over there, e to the power of minus RT. Yes, that's it. And then initial setup cost of portfolio or the covered call portfolio will be like this. And then this should be, right, the value of this portfolio should be the present value of risk-free cash flow, the present value being here. Discounted at risk-free rate R, and then, right? So call option value will be nothing but this. If you do the arithmetic, yeah, keep this guy or send this guy to the other side of the equation and this guy to the other side of the equation, you will figure this out. Okay, and since this delta hedge ratio is like this ugly term, it will lead you to the following page. And then it will screw up your eyes. Don't move right now, okay? But what we want to do is we want to transform this equation over here about the call option. We want to transform our call option formula into this form. Okay, what the heck will be going on in the future in the next slide? We're going to do some present value calculation. You see this over here. But what's the present value based on? The two different cash flow at the end of the maturity. Upstate, downstate. Call option value in upstate and call option value in downstate. And then we want to get some kind of a weighted average or probability looking like, right? Probability like things, weighted average of this up value and down value of call option. Okay, why don't I say probability over here? Well, because this is not the actual probability in our world of risk averse persons. Okay, it's kind of a probability in the sense that it sums up to be 1. Well, P and 1 minus P will be there, so that it will sum up to be 1, right? Upstate, downstate. But it's not the actual probability, but we will call this risk neutral probability, as if this is the probability in risk neutral world. Risk neutral world, where the heck is that? This is the risk averse world. Everybody's risk averse. But mathematically, it will give you some idea that it is as if everything is done in risk neutral world. Everybody's preference is risk neutral. I showed you this expected utility graph, right? It should be linear in that world, right? Why do we need that? Well, because we want to, in the risk neutral world, you don't need risk premium to discount any cash flows. Everybody, all the cash flows, no matter how much risky that is, it will be discounted at risk-free rate, so that mathematical job will be a lot easier over there. So we are going to try to rewrite everything so that it will show up something like cash flow up, cash flow down for call options, and P times 1 minus P format. Okay? Right. Yeah, which will be like this, discounted at this. This is more discrete time, one-time discount rate, right? Whereas over here is continuous compounded version. Okay? So I will screw your eyes just once in your lifetime, but don't get mad at me. Okay? This is what financial engineering is about anyway. So in this slide, you see your call option value, okay? Starting from what we had in previous slide, okay? Over here, right? Over here, this guy. Well, we are replacing the delta with this ugly term over here. And then if you do arithmetic, right? And then you will be able to find out that it finally looks like this. I'm not going to go through this one. I'm not going to ask you to go through this derivation part in your final exam or midterm exam, right? Don't worry about it. But just for those of you who are more mathematically inclined, right? So this works like that, and then it sums up to be like upstate, downstate cash flow with some probability-like weighted average, right? Going on there. And this probability-like thing, we're going to call this risk-neutral probability, right? Risk-neutral probability. And then that's what we call risk-neutral pricing. In the risk-neutral world, you can discount those with risk-free rate, okay? Upstate rate is 1.1, downstate rate is 0.9, risk-free rate is 12%, and per year, it's a quarterly basis, so divided by 4, and cash flow up and cash flow down is 1 and 0, and what? The probability, risk-neutral probability will be like this. So up minus down, that's 1.1 minus 0.9, 0.2, and then here is like 1 plus risk-free rate if it is like a discrete time method. Continuous compounding is like e to the power of 3%. That's this guy, and then minus down rate. Okay, so that's that. That's risk-free rate 65%, and 1 minus P would be on the other side. Now, this is equivalent to this ugly term. If we don't do continuous compounding, P can be interpreted as probability of an up movement in stock price. The value of the option today is its expected payoff discounted at risk-free rate. Why risk-free rate in this case? Because we are assuming kind of a risk-neutral world. You don't need risk premium. So expected value of S sub T, big T, right? So at the end of the maturity, the stock price, expected value of this guy will be nothing but today's stock price with up rate and down rate weighted average by this risk neutral probabilities for each different states of nature. And then you do the arithmetic, you will realize P times this thing and the S0 times D will be on your right hand side. And then since risk neutral probability is like this, if you stick in over here, right, and do the math, right, do the math, then you will realize that your expected value of maturity stock price is nothing but your current stock price growing at risk-free rate. Ooh? I told you in the risk-free, risk-neutral world, you discount any kind of risky asset, okay, at risk-free rate. That means the flip side of it is the future value, expected future value, is nothing but today's price continuously compounded growing at risk-free rate. Growing at risk-free rate, that's what's happening over here. Expected rate, expected value, and 1 year from now is today's price growing at risk-free rate. Risk-free growth. The risk may be over here and there, but on average, risk-free growth is happening. Now, why do we try to say this one? Well, this one shows that the stock price grows at average at the risk-free rate. We are assuming a risk-neutral world. When we set the probability of an up movement to P, the value of the option is its expected payoff. In a risk-neutral world, it is counted at risk-free rate. And this has awful similarity. Right? This looks awfully similar to our discussion in our previous chapters about the forward rate and spot rate relations, right? This is equivalent to, in the FX market, this is equivalent to forward rate at the end of maturity based on spot exchange rate as 0. Recall that your forward rate is nothing but our expected value of your spot exchange rate at the end of maturity, big T. Yes, that's this guy. And should be what? Equal to S0 of your spot rate times this ugly term was our the IRP relations, right? And this IRP, right? This is your, what is it? Risk-free rate in a certain sense. And we just have the risk-free rate differentials over there. So we're going to get there in our FX options or futures options discussion. So wait for that. We interpret foreign currency as a stock whose dividend yield is the same as the interest rate of the foreign currency. Okay, so dividend yield. This is a US perspective. Domestic currency on your numerator, foreign currency on your denominator. Pound, hello foreigners, and then dollars is domestic currencies in this perspective. So this is risk-free rate, and this works as a dividend yield. If you remember Black-Scholes option pricing model, dividend yield is something subtracting out from your rate, right? Risk-free rate. So wait for that. Okay. Now that's our refresher of mathematics and then option pricing. So the next video we're going to go into the FX futures option pricing models, right? So hope you liked it, and then like and subscribe. Thank you for watching.